Hello, and today I want to work through some balancing and stoichiometry problems for you. So this is coming from one of the homeworks I've created, homework number 3, and let's go ahead and work through it a little bit. So the question states, acetylene torches are commonly used in welding and metal cutting because they can reach temperatures of about 3,500 degrees Celsius. The general guide for using an acetylene torch is 2-to-1 ratio for oxygen to acetylene. Balance the combustion reaction below, and it gives the reaction. And then, does this general rule of 2-to-1 for oxygen to acetylene hold true? Well, to start off, let's go ahead and balance the reaction. So I'm going to break up our reactants and products, and I'm going to look at each individual element. So I'm going to look at carbon, hydrogen, and oxygen. So looking at the carbons, we can see that we have a 2 subscript here. So that's going to give us 2 carbons overall for the reactant side. And then on the product side, we only have CO2 here, and there's nothing written down here, so it's assumed to be 1. And so we only have 1 carbon. So to make these balanced, I'm going to add a 2 coefficient in front of the CO2, and that will change our product side to having 2 carbons. So now our carbons are currently balanced. Now we're going to look at the hydrogens. So for the hydrogens, we have 2 hydrogens over on the reactant side, and we have 2 hydrogens on the product side. So both those are going to be 2, and currently they are balanced. Now we're going to look at the oxygens. Now for the oxygens, we have O2 here, so we have 2 there. And then on the product side, we have our 2 coefficient here and this 2 subscript. These are going to be multiplied together, so we're going to have 2 times 2, giving us 4 oxygens from the CO2. And we also have this 1 extra oxygen from the H2O. So you need to look at every single compound when you're looking at this. So on our reactant side, we had 2 from the O2, and then on the product side, we had 2 times 2, giving us 4 from CO2, and 1 times 1, giving us 1 from the water, giving us a total of 5. Now, unfortunately here, since we have this 2 on the reactant side, there's no way for us to get to an odd number, such as 5. Coefficients have to be whole numbers. We could put down 5 halves, but that's not really a proper thing to do. So when you find yourself in this situation, the easiest thing to do is just multiply everything by 2. So I'm going to multiply our acetylene by 2, so 2 times 1 is 2. Our CO2, 2 times 2 is 4. And then the water, 2 times 1 is 2. And so now we'll go back and reevaluate everything, and then we'll try to figure out what we can do for this O2 over here. So looking at our carbon, we have 2 times 2, giving us 4, and 4 times 1, giving us 4. So both these are going to be 4. Then we can look at our hydrogens. So we have 2 times 2, giving us 4, and we have 2 times 2, giving us 4. So both the reactants and product side for hydrogens are going to both be 4. Now we can look at our oxygens. We didn't put a coefficient here, so this is still going to be 2. But on the product side, we have 4 times 2, giving us 8, and 2 times 1, giving us 2, for a grand total of 10. 8 plus 2 is 10. So in order to get our reactant side up to 10, I'm going to multiply this by 5. So I have 5 times 2, and that will give us 10 as well. So now our reaction is balanced, and we can move on to trying to answer the real question. So does the general rule of 2-to-1 oxygen to acetylene hold true? And there's a couple ways you could answer this. First way you could do is you could say, no, it doesn't, because the ratio is 5 to 2. So our oxygen has a coefficient of 5. Our acetylene has a coefficient of 2. So the ratio is just those numbers, 5 to 2. All right, it's a 5 to 2 ratio of O2 to acetylene, C2H2. All right, that'd be one response you could have. Another response one could say is you could say yes, because a 2-to-1 ratio is similar to, you could either say a 5-to-2 ratio, or if you want to make it a little bit more apparent, a 2.5 to 1 ratio. And the other thing is, this is a starting point. So normally what will happen whenever you actually are using a acetylene torch is, normally this rule of 2-to-1 is what most people say and do, because it does hold mostly true. It's a little bit easier to remember 2-to-1 as opposed to 5-to-2 or 2.5-to-1. And the other thing is if you're doing this, you're going to be using a little bit more acetylene. It'll be a little rich in your acetylene and a little weaker in your oxygen. And so for part of this, we have some oxygen in the air, typically when we're doing acetylene torches, unless you're out in space. So we're getting a little bit of oxygen from there as well. And so this is actually a pretty good little ratio to start out with. And it'll also start out with your flame a little bit weaker so that you can finally tune it to get up to that really high temperature and make a really solid flame. Anyway, so those are two responses you could have for this type of question. So let's go ahead and we'll move on to another question, question number 2. All right, and it reads, while babysitting your little brother, he exposed your mother's finest silverware to a rotten egg. You are charged with cleaning the sulfur tarnished silver with a roll of aluminum foil. There is 0.24 grams of silver sulfide on your mother's prized silver. She tears off a 5.00 milligram sheet of aluminum foil and tells you to get to work. We have the unbalanced chemical reaction shown below. And we have to determine how many grams of aluminum are needed to clean the tarnished silver. And then should you use just a single sheet your mom handed you? Briefly justify your response. So the first thing we want to do is we want to go ahead and balance this reaction. So we're going to break it up into our reactants and products. And so we're going to be looking at silver, Ag, sulfur, and aluminum. So I'm going to start off with silver. All right, and this may not be the best way to go about balancing this one, but I want to do it so that we can kind of showcase something. So we have 2 silvers here, and so I'll put them on my reactant side, and on the product side we only have 1. We have 1 silver. So in order to make those balance, I'm going to go ahead and put 2 coefficient here, and that will now be 2 silvers. Now we're going to look at the sulfurs. So when we look at the sulfurs, we'll see that we only have 1 sulfur on the reactant side, but we have 3 sulfurs on the product side. So we'll put a 3 there. And in order to get that to be balanced on both sides, I'm going to need to add a 3 coefficient in front of the silver sulfide. And so that will change my sulfur to be 3, but now I need to adjust my silver. So my silver is now 3 times 2 for a total of 6 silvers. And so now I need to adjust our silver on the product side. So instead of this being a 2 coefficient, I need to change this to 6. So we have 6 times 1 is equal to 6 silvers. So now our silvers are balanced, our sulfurs are balanced. And one thing to keep in mind with this is, as you're doing this, you can put coefficients in there, change them, cross them out, try again. It's just each time you change coefficient, make sure you go back and evaluate all the elements you've already looked at once before. All right, so now we can look at aluminum. And on aluminum, we have 1 aluminum. And on the product side, we have 2 aluminum. So we'll put a 2 there. And to make this balance, I'm going to put a 2 coefficient in front of the single aluminum. And so now we'll have 2 aluminum. So now looking at all of our elements, it's balanced. The reactant side matches the product side for each element. So now we can move on to answering our real question. So we want to determine how many grams of aluminum are needed to clean the tarnished silver. So we have several numbers given to us in the problem. We want to make sure that we're looking at the right one. So if we're trying to figure out how much we need to clean the tarnished silver, we want to look at how much tarnished silver we have. So we have 0.24 grams of silver sulfide, or tarnished silver. So that's what we want to use for our numbers. So I'm going to set up a little railroad cross method here. So we're going to start with 0.24 grams of silver sulfide. And then diagonal down from here, we need to set up something else with silver sulfide. So the easiest way to go about doing this is to look at your periodic table and determine the molar mass. Normally this is a really good go-to if you're a little stuck or you don't know where this stuff is coming from. So we want to get to moles, and so in order to do that, we're going to use the molar mass. So we're going to look at silver right down here. It's in the transition metals, and we see it has 107.9. We're going to put this down on silver. We have 107.9 grams per mole. And in this molecule, we have 2 silvers. So we're going to multiply that by 2. And so that will give us 8, carry the 1. 14 will now become 15, carry the 1. And then we should end up with 215.8 grams per mole coming from our silvers. Now we need to look at the sulfurs. So for sulfur, we need to find out on the periodic table, and it's located right over here. And so we'll see that it's got 32.07, so that's 32.07 grams of sulfur for every mole of sulfur. So 32.07 grams per mole. We're only using 1 sulfur, so we just have to multiply by 1, giving us 32.07 grams per mole. Now we can add those up together, and we'll get a 7, 8, another 7, 4, and 2. So we're at 247.87 grams per mole. And if we want to look at our significant figures, we're good down to the tenths and the hundredths. So we're going to be limited to the tenths. So we'll be good down to that first 8. So now we're going to just plug this into our spot here in our railroad cross method. So we'll say 247.87 grams of silver sulfide for every 1 mole of silver sulfide. All right, so now that we are in moles, we can use our chemical equation. And looking at our chemical equation, we can see that we have 3 moles of silver sulfide. So we need to also figure out what we're trying to get to. The question asks for aluminum. So we're going to say we have 3 moles of silver sulfide for every 2 moles of aluminum. And whatever these coefficients are, I say just use them. So if you're balancing out this chemical reaction and you ended up with double all those values, it still works. And I'd recommend just using whatever coefficients you have written on there. So we're going to say 3 moles of silver sulfide for every 2 moles of aluminum. So now we're in our desired species, and now we just need to get to our desired units, in this case grams of aluminum. So again, we can use our periodic table here. We'll look at aluminum right here, and we'll see that it's at 26.98 grams per mole. So I'm going to say for every 1 mole of aluminum, make sure our units are canceling out, 1 mole of aluminum, we're going to have 26.98 grams of aluminum. And so if we go through and we multiply everything on top, so we'll do 0.24 multiplied by 2, multiplied by 26.98, and then we're going to divide that whole thing by 247.87 and divide that answer by 3. We will get a answer out. Let me get rid of my periodic table here. We'll get an answer out of 0.017415581 grams of aluminum. Now we want to look at our significant figures. So from the problem, we were given 2 sig figs for our grams of silver sulfide. We're going to have 4 sig figs from our molar mass. This is an exact equality, so that's not going to affect anything. And then we have 4 sig figs from our other molar mass. So we're going to be limited by the lowest one, which is 2. So we'll go 1, 2. And so we're good down to the 7. So writing this out, we'd have 0.017 grams of aluminum are required to clean up the tarnished silver. Now to answer this question, part B of this question, should use the single sheet your mom handed you and briefly justify your response. Well, we could say no, we need 4 sheets, because this will take just over 3 sheets to remove all the tarnish if each sheet is 5 grams. So we could say no, we need 4 sheets. Another response you could have is you could say, well, yes, that's what mom told us to do. So again, always justify your responses, but you should get out 0.17 grams of aluminum. All right, that's what we were told. Anyway, hopefully you found this useful. I'm going to skip question number 3 for now because we haven't quite covered how far or how to determine where the electrons are coming from in a voltaic cell. So we'll save that for later. All right, but hopefully you found this useful, and I look forward to seeing you in the next video.